Today we're going to be taking a look at this G5 from the IMO 2024 shortlist. And just a disclaimer, as I've put in the title, this is actually, in my opinion, a really good angle chasing practice. There's basically no other concepts we need, just angle chasing. So we have a triangle ABC with incenter I, we have a circumcircle of ABC, and then we construct a circle that's passing through BIC, and as we know from some theory, this also passes, it is centered at the midpoint of minor arc BCM. And then we select a point K somewhere. We then draw the angle bisectors between the two lines AK and BC. And then these two lines intersect the circumcircle of BIC at 4 points. W is the top left, Y is the top right, Z is the bottom left, and X is the bottom right. And we are asked to show that angle WAY is equal to angle ZAX. So to solve this problem, we first need to untangle this condition just a little bit. And to do so, we actually need a bit of intuition here, which is to notice that Z and Y, first of all, Z and Y lie on the same line, and W and X lie on the same line. However, there doesn't seem to be much relation between the points Z and X, for example, or W and Y. So it is quite natural for us to think maybe we could just separate out WX and ZY by themselves and not have to deal with the relationships between each of them. For example, if we find something out about ZY, by symmetry, the same thing can be said about WX. So maybe we can just prove something about ZY, let's say. So what do I mean by that? In order to prove that WAY is equal to ZAX, we can split these two angles up a bit. For example, WAY is equal to WAK plus KAI plus IAY, right? These three angles. So let me write that down. The first angle is equal to WAK plus angle KAI plus angle IAY. And the second part is for ZAX is essentially the same thing, because this is just angle ZAK plus this angle KAI plus the angle IAX. Okay, we want to prove that these two quantities are equal, and obviously the angle KAI's cancel out. So we just want to prove that this plus this equals this plus this. And here we actually need to make a bit of a leap of faith, which is that we hypothesize that angle ZAK, this angle, actually looks quite a lot like angle IAY, which is this angle right here. Well, if we prove that this is equal to this, then obviously this will be equal to this, so our problem is solved. And as it will turn out, this hypothesis is indeed correct. And so our problem just reduces down to proving that the angle ZAK is equal to the angle IAY. Just a quick word on the intuition here. As I've noted before, the ZY and WX pair leads us to find this relationship that we want to prove, but also we can notice that, for example, ZAY and ZAX and WAY share the common angle here, KAI. So it also helps with the intuition, because if we write it out as a sum including KAI, then we can cancel out KAI, obviously, as we just did there. So it remains to prove this. And since we only want to do Z and Y and W and X will be equal by symmetry, we can actually remove W and X from the picture. That's one benefit of doing this, trying to prove this instead of our original statement. And so what we are going to do is we will draw a new diagram down here. So what I've done in this new diagram is, first of all, I removed WX, and then I drew a circle and added 2 more points. I drew a circle center at S and added 2 points P and N, but we will get to that a bit later. So first of all, in order to prove that ZAK is equal to IAY, we should obviously look at the triangle ZAY. If we look at the triangle ZAY, ZAK equals IAY is the same as saying that AP and AM are symmetric, or sorry, not AP, AK and AM, well, it's technically AI, but AI and AM are the same thing. We want to prove that these two lines are symmetric about the angle bisector of A. And to do that, we will draw the angle bisector of ZAY, which is this line here, and we let it, well, let's define N later. Let's just draw this angle bisector first, and then we draw the line AK, we extend it down, and we'll also worry about the definition later. But essentially what we want to prove is that this angle equals this angle. Since this is the angle bisector, that will imply that AP or AK and AM are symmetric about the line. And so we have that the two angles we want to prove are indeed equal. Okay, so since we are considering the triangle AZY, it obviously makes a lot of sense for us to draw the circumcircle of it, which I have done here. The circumcircle of AZY is this new circle I've drawn that's centered at this point S here. And I'll extend the line AK down here to intersect the circumcircle of AYZ at P, and then we draw the line, the angle bisector, to intersect the circumcircle at point N. And so that, I think that explains everything in this figure that I've added, which is the circumcircle, point P, and point N. And so now what we want to prove is that PAN is equal to NAM, or equivalently PAN is equal to half of PAM. As it will turn out, the second expression is easier to prove, so we can discard the first one. Okay, so we want to prove this. And how do we do so? Well, first of all, notice that PAN, before we do anything, let's look at the point P. We define P to lie on the circumcircle of AZY, but it seems that it also lies on this circle. Well, that is true by a little bit of power of a point or radical lemma. So, for example, if we look at the point K, K lies on the line BC, which is the radical axis of these two circles. This means that if we draw a chord passing through K on this circle and intersects at these 2 points, and then we draw another chord passing through K on the other circle passing through these 2 points, we know that these 4 points have to be concyclic. That's called Radical Lemma, which essentially just says that these 4 points are concyclic if and only if this, this, and this, which is the radical axis, are concurrent. And that's the converse of the forward direction. And so P indeed lies on this circle. And so our quantity angle PAN is just equal to half of angle PSN. So it would be quite nice if we could prove that PSN is equal to PAM. Well, it wouldn't be quite nice, that's exactly what we want to prove. But if we take a look, S, N, and M are actually collinear. Well, why is that? We know that this is the angle bisector, and so N is the midpoint of arc ZY, and so SN is perpendicular to ZY, but since Z and Y are both on the two circles centered at S and M, SM is also perpendicular, so these two are the same line, so SN and M are collinear. And here we've actually already sufficiently used the angle bisector information from the line AN. So we have that PSN is actually just equal to PSM. And we want to prove that PSM is equal to PAM. Well, that's essentially just trying to prove that PSM equals PAM. That's just trying to prove that PMAS are concyclic, which just means that S lies on this circle. And as we can see from our diagram, well, this diagram is supposed to be perfect, so we can see that S does indeed lie on it. But if we draw an accurate diagram ourselves, we should also be able to guess that S lies on the circle. So all that is remaining is to prove that S lies on this circle. And how can we do that? Well, if we take a look, S, O, and M are the centers of these three circles. So maybe we can do some angle tracing around these centers. Specifically, maybe we can try to prove that OMS is equal to OSM. Okay, so let's look at OMS first. We have that OM is perpendicular BC. We have that MS is perpendicular to ZY. And so if we think about this angle, we can transform the line OM to the line BC, transform this line to the line ZY, then this angle that we're trying to find is just this angle, which is YKC. Let's write that down, YKC, which we want to equal to the other quantity, OSM. And we can actually do the exact same thing over here. OSM, we have that OS is perpendicular to AP, and SM, as we mentioned before, is perpendicular to ZY. And so OSM is just equal to, we have OS transformed into the line AK, and SM transformed into the line ZY. So that's just equal to AKY, angle AKY. And this is the most exciting part because this is actually where our angle bisector condition comes in. YKC is this angle, AKY is this angle, and the problem's condition tells us that this line is what bisects the angle AKC, therefore they are indeed equal, which means that indeed OMS equals OSM, and so OM is equal to OS since it's an isosceles triangle, and so S indeed lies on this circle. We can do the tracing all the way back to our original statement. For example, from here we can go to prove that this is equal, which will go up to prove this and prove our original statement. Alright, so that's a G5 problem done. And well, I wasn't lying when I said it was only angle tracing. What about the key takeaways? So for me personally, to find that the point P lies in the circle, I kind of failed to observe that, and I think it will be really helpful for all of us to be more familiar with these kinds of configurations. This is actually quite similar to another video, the configuration in another video, which I'll link up there. In that case, it was slightly different. It was that we have these two circles, and if we have a point here, then if we draw any two lines passing through this point and it intersects these two circles at these 4 points, and these 4 points are concyclic, so that is the case when the point is outside, and this is the case when the point is inside. But in general, what it's essentially saying, this is just radical lemma. I'll actually go a little bit more in depth on this in this video. So when I learned radical lemma, what I was told was that 4 points, if we have two circles and 4 points, these 4 points are concyclic if and only if their intersection points lies on the radical axis. And so this by itself obviously is very helpful, but I think I found a bit of another way to think about it. So if we just have something similar, let's say we have a point on the radical axis of here, essentially it's just equivalent to saying that if we go from this line, we draw a ray down here, intersects at these 2 points, and then we draw a ray down here, intersects at these 2 points, and these 4 points are concyclic. And it doesn't really matter because we can rotate this line all around, it can intersect at any 2 points, but no matter what, the 4 points will always be concyclic. And this is actually what we can see here, because point K lies on line BC, and if we draw this line, it intersects at these 2 points, draw this line at these 2 points, then these 4 points are concyclic. That's the first takeaway I wanted to mention about the radical axis. And the second thing I found quite interesting in this problem was about the manipulation of the centers. So the first part, after we proved that P lies on here, the first part was just to direct the angle back to, for example, PAN to PSN to PSM, and we essentially just want to prove that S lies on the circle. And we did that by showing angle OMS equals angle OSM. And we transform these angles from between these centers to something between the lines or the radical axes of the circles, because we know when we have two circles, their centers, the line is perpendicular to this. So we can actually transform these angles around to the radical axes, and that will turn out to be really helpful, as we've seen in this problem.